So our second speaker today is Jules Lamer. He is going to talk about Heisenberg spin chains and long-range versions of it.
All right, I'll give the last few arrivals time to find a seat. So first, I'd like to thank the organizers and especially Filippo for this beautiful workshop. And it's a great pleasure to be here. I'm very happy that the weather is also cooperating. And indeed, today I'll talk about the Heisenberg spin chain, which I suppose is known to everyone, and its long-range friends. So I like long-range quantum integrable spin chains. And I want to argue that Heisenberg spin chain naturally sits in the long-range world, really, and it's kind of a special nearest neighbor point, but it's kind of quite interesting to view it in the context of long-range spin chains. And this is based on work with Rob Klabbers, who's a longtime collaborator. He's in Berlin now, and with Vincent Pasquieu and Sidina, who are both here. Right, so the big landscape that I like to show is this one here. So this is kind of a landscape of long-range spin chains. So on the left column, we find the Heisenberg spin chains, which we know pretty well. It comes in 3 levels. There's the basic, the isotropic version, the Heisenberg XXX model. Then there's a partially isotropic version, which is the XXZ. Oh, and then there is the totally anisotropic model, which is the XYZ. So the further you go down, the more spin symmetry there is. Now, there's another axis here, which is the long-range axis. So here we're in the nearest neighbor kind of area, but we can turn on long-range interactions, at least in the isotropic level. And then you can go from Heisenberg via what's called the Innocence spin chain, which I will introduce, to another fairly well-known spin chain that is the Haldane-Shastri model. And this also comes with an XXZ-like version, the Q-deformed Haldane-Shastri model. And there are notably some empty ports in this map. So really one of my long-term goals is to try to understand what is happening in this blank area of the map. But today I would like to tell you about kind of 2 ways that the Heisenberg models are related to long-range spin chains. So the first one is this isotropic level, so that will be the start. And then later I'll actually talk about a slightly different version, which will be related to the Q-deformed Haldane-Shastri, but it's another deformation, which is not quite on this map of Heisenberg XXZ. Let's see, all right. So here is a typical anatomy of a spin chain. So for simplicity, let's take L sides with spin 1/2 only. So Hamiltonians typically have this type of form. So it's for long-range spin chains, it's a sum over pairs of sides, I and j, like here on the spin chain. And each side has this long-range spin exchange interaction, 1 minus the permutation. So it's an anti-symmetrization spin exchange interaction. And then spins that are further apart might interact less strongly. So there's a potential function here which dampens the interactions at longer range. And the potential function determines the long-range behavior. Let me note that this spin chain, these type of spin chains, they're isotropic, so they commute with Sl2 or Su2 if you wish, because of this structure of the spin interactions. And then they're also homogeneous because this potential here depends on the distance between I and j along the circle. So here I mean the distance on the, well, z modulo Lz if you wish, the circle with circumference L. So since it only depends on the distance between these 2 sides, this potential becomes translationally invariant, and so there's a action of translations which commute with these type of Hamiltonians. So some important examples, which I mentioned just before, are the Heisenberg spin chain, for which this potential just forces the 2 spins to be adjacent. So there's a Kronecker delta, this potential function, and you get a nearest neighbor interaction. So everybody knows and loves this spin chain. On the other side, there's another kind of rather nice point, which is in which the potential is basically 1 over the chord distance squared, which is this dot, so 1 over the square of this dashed length here of the distance, the chord distance between the 2 spin sides. Or if you want normal coordinates, then it is basically 1 over sine squared of this distance along the circle rather than through the middle. Okay, this is a Haldane-Shastri spin chain. It was found in the late 80s, and it has a lot of very beautiful properties that I'll outline later. So although this Hamiltonian looks a little bit more simple, a little bit more complicated than that of Heisenberg, it turns out that actually the physics, the behavior, and the mathematics, the representation theory of this model is very, very beautiful. And this model is actually simpler in some sense than the Heisenberg spin chain. Now, there is a more or less well-known intermediate spin chain here, which is called the Innocence spin chain. So this was found by Innocence, and it is rather more subtle than either of its limits, but it is an interpolation between the two. So the potential in this case is a Weierstrass P function. So it's an elliptic function. It has two periods. The one is the length of the chain to make sure that we're L periodic, like the 1 over sine squared is L periodic. And the other one is a purely imaginary period, which is traditionally parameterized by I pi over kappa. And I take kappa to be a positive real number. And this kappa sets the interaction distance. So if I send kappa to infinity, then this, if I put the right constants here, precisely becomes, on the lattice, becomes this nearest neighbor pair potential. So basically this Weierstrass P function spikes very sharply and we only have interactions between nearest neighbors. Then if kappa becomes lower, 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 we get this general Weierstrass P function. And then if kappa goes all the way to 0, we remove this imaginary period. We send it to I infinity. And we get this 1 over sine squared here. If you would want, so the way to think about this Weierstrass P function is it contains this 1 over sine squared. And actually, if you would send L to infinity instead, so you remove the real period, then you get 1 over sinh squared, which indeed has a periodic, an imaginary period. So you kind of think of this Weierstrass P function, if you've never seen it before, as kind of a combination of 1 over sine squared and 1 over sinh squared, two periods. Bernard?
What is the, is it essential that the period is rectangular? What happens when you make it?
It's convenient and it's, I don't know if it's essential, but it is certainly the standard way to do it. And I've never really thought about why, but I think this contains really everything that we want in terms of this picture here. So of course you could play with this, and actually there are lots of things that you can vary in this picture. But here I want to focus on the basic kind of case. Probably there might be relations for hermiticity and so on. That might be quite true, but I am not sure. I have to think a bit about that. All right, so these type of spin chains, they have this isotropy, so Sl2 invariance, and homogeneity, so some action of the integers by translation, periodic cyclic translations. So it means that the Hilbert space has this kind of nice structure. We can just use the representation theory to understand part of the structure of the Hilbert space. So here I've drawn basis vectors for the Hilbert space. So each dot represents a one-dimensional subspace, and I want to use the symmetries to kind of group them in a nice way. So firstly, I want to use this Sl2 symmetry. So Sl2 has a spin raising, a spin lowering, and a spin z component. Spin z here just measures, so this vertical axis is the spin z value. So here I denote by m the number of down spins, or if you want the weights, I gave the weights here. So it's a weight space decomposition, these different levels here. And then the raising and the lowering operators allow us to go up and down between these vertical strings of one-dimensional vectors, right? So each of these kind of vertical strings here is irreducible for Sl2. And so by Sl2 symmetry, it suffices to find these red dots here, which are the highest weight vectors. Of course, if you have 0 down spins, then we know which vector it is. It's just a vector with all spins up. And so we understand immediately this entire L+1 dimensional irreducible. So this is what Sl2 gives us. We need to find what these red dots here are. So now we can use an extra symmetry, which is that actually we have this translational invariance. So this actually fixes these red dots here. They're called magnons. This is their explicit form. The wave function is just a plain wave here with some value p here. It's such that the cyclic translation x by e to the I p is called the momentum, and it has to be quantized because we're on a circle. And then since these are L minus 1 if you forbid p is 0 eigenvectors, you get all of these vectors here. So they must be eigenvectors of the Hamiltonian as well. You can act with the Hamiltonian on these vectors and you find their energy. And if you think of this energy as a function of this momentum, then that function is called the dispersion relation. Sorry? In these cases, yes. I'll show you in a moment what they are. So because of these two symmetries, really the job is to understand these red dots here. So I want to say a little bit more about this. So usually we use some sort of beta ansatz, and indeed this can be done here. So that will be the next point. But let's first show what so this is just the dispersion. So here I plotted the energy up and the momentum from 0 to 2 pi horizontally. So here's the momentum, here's the momentum, and here's the momentum. This is the Heisenberg point. Here is Zemtsev, or maybe kappa is 1 or something. And then here is Haldane-Shastri, where I removed the imaginary period. And so here you find this dispersion is just the sine squared that you know from the beta ansatz. Here it is some more complicated elliptic function. And then here it becomes very nicely for Haldane-Shastri a parabola. So it's a half p times 2 pi minus p. So it's just a very beautiful parabola that's 0 and 0 and in 2 pi. So this is a very nice dispersion of Haldane-Shastri. This is one of the first signs that something special is going on here. And this was the eigenvalues for the M1 sector. So let's go back to this picture. This is the eigenvalues of the Hamiltonian on these dots here. But in fact, by Sl2 symmetry, it's also the eigenvalues of these dots here, right? We know by Sl2 symmetry, we actually know what all of these dots here are because we just applied the lowering operator. So here, I really want to focus on this 2-particle sector. This is the first time that it starts to become a bit more interesting. Luckily, it's much simpler than more than 2 particles. So for now, I want to really focus on the 2-particle sector and show you that actually this has a very nice structure. So we understand so what we have to do is we have to solve these Betti equations. I don't really want to go into details, but the point is that we have some equation for what are called the quasi momenta. We think of them as the momenta of the separate downspins, and they're such that the sum of these two, P1 and P2, is the total momentum that I had before. And these quasi momenta, I would like them to be 2 pi over L times an integer. That would be what happened for the magnons in the free theory, but this is an interacting model, so there will be some correction because of the interactions, and there's some known scattering phase function, which gives us this modification of the value of these quasi momenta because of the interactions. And then these integers, so what I need to do is so this theta is a known function. I don't want to give it here, but I want to give for each value of integers, or for each suitable pair of values of these integers, I need to solve this beta ansatz equations. And so if I take my first integer, so I can order them without loss of generality. And if I take my first integer to be 0, then I can show that there's a solution for which the first quasi-momentum is 0, the second quasi-momentum is kind of the total momentum, and it is just 2 pi over the length times an integer, because in this case there's no interaction. So these are these descendants that I mentioned before. And maybe I should mention, sorry, that these we know, of course, explicitly what these what this elliptic function here is. Now, the next case is we have to look at these red dots, right? The highest weight vectors, and they come in 2 types. So first, I want to focus on the simple type, and you can call them scattering states. So if these 2 integers are not equal and not neighboring, but sort of sufficiently far apart, then you can check that there are L-2 choose 2 of such pairs in this range. And for each of these pairs of integers, non-zero, there exists a unique real value of this scattering function. So if you numerically solve the beta ansatz equations, you get a unique value here for Heisenberg, which is quite small. So it means that these quasi-momenta are actually slightly pulled towards each other. So they kind of attract each other a little bit, but they're not very far from these 2 pi over the length times integer values. So the interactions are quite weak in this case. And if you look at the wave function, you can interpret this as a scattering state in the sense that the magnons are typically kind of going around the circle, and they feel each other a little bit, but they kind of scatter along each other. And of course, this is finite length, so it's not proper scattering states, but it's kind of a good way to think of them. And if you look at the energy, since the quasi-momenta are so close to their free values, the energy is very close to the sum of those 2 free energies. And here I've plotted both the values, the actual values of the energies, and the sum of these 2 free values. So you see that the energies are actually slightly higher, but only slightly so. This is for length 26 or so. So these are all the possible scattering states for Heisenberg. Now, if you turn on Innocence, it turns out that this scattering, this phase here is going to decrease a little bit. So actually the values, the quasi-momenta are going to get closer to their free values, the interactions. So as we turn on the long-range interactions, the quasi-momenta become closer to being free. So the energy also becomes closer to just being the sum of the 2 free energies. And I mean, the true values of the energy for the free quasi-momenta. And you see that these dots are closer to the open circles than they were here, if you look very carefully. Another thing that you see maybe is that here the dispersion went right through this sort of envelope of the scattering states. Here, I don't know, it starts to unfold a bit, so stuff is going to happen. Now, quite interestingly, if we send kappa all the way to 0, so we really get this long-range model where we had 1 over the sine squared, then it turns out that these quasi-momenta, they become precisely 2 points over the length times an integer. So this model is in some sense free. These two magnons, they don't really feel each other, except for the rule that they cannot be equal or adjacent here. Remember, this is the case of integers that we're looking at. And the energy, as a consequence, is literally the sum of the two separate energies. So this is really nice. So you see that here the circles and the dots really completely overlap. This is an extremely regular and nice spectrum. And you can check that, for instance, if you choose here the second quasi-momentum and here, I don't know, the 10th, then at the 12th quasi-momentum, there will be a dot, which is precisely the geometric sum of these two vectors. It's really the sum. So this is a very nice property of Haldane-Shastry. And the scattering phase, let me emphasize again, is 0 for Haldane-Shastry. Now so if you really do the counting, you notice that we don't quite have everybody yet. So there's few solutions that we still need to find. And they're more subtle. My computer's taking a while. There they are. So now what we do is we need to take the first integer again positive, and the second integer should be either equal to the first or the first plus 1. So they should be either coinciding or just next to each other. And then we have to take suitable values of these so that we get the remaining L minus 3. We can kind of classify very nicely how to do this. And then it's more interesting. So what happens if the length is low enough? I don't want to go into larger length unbinding kind of issues. There is a unique value of the scattering phase for Heisenberg, so that the two quasi-momenta are each other's complex conjugates. So the real part is just so that they maybe become the average. They really sit at the average of these two free values. And then there's some positive real part for P1, let's say, and then this is the complex conjugate of P1. And it turns out that the energy of this is roughly half the energy of if you would take the total momentum. So in fact, here you get basically half times the dispersion relation, and it's not quite true. For if the length would go to infinity, then really the bound state curve becomes half the dispersion, but it's extremely good approximation even for finite length. So the interpretation here is that they are bound states, because if you look at the wave function, then typically the two downspins tend to be very, very close to each other. There's a strange exceptional case in which they're actually kind of antipodal. So they're a bit like a Lagrange pair where one is kind of moving precisely on the opposite side of the other, but that's again a detail. So let's call these bound states. Now, if you turn on long-range interactions, then because of we have an elliptic function now. So so this was 2 pi periodic, which is related to the L periodicity of the chain. But now the Weierstrass P function also had an imaginary period, and it means that these quasi-momenta also get an imaginary period. So in fact, what I can do is I can either go from minus I kappa to plus I kappa, so this fundamental parallel domain, or I can take the opposite, the positive half plane. I can take this thing. So let's, instead of P2 being here, think of P2 as being there by 2I kappa periodicity. So now what's going to happen, and we looked at this quite carefully numerically and so on, for MS2, is that these, as the interaction range increases, these two quasi-momenta, they get closer and closer to each other. At some kind of critical value of kappa, they're going to bounce. This is not physically significant, but we can write down an equation that determines this value. And then what happens is that one of the quasi-momenta moves to the left and the other to the right. This is what Didina mentioned the other week. There are two types of bound states. One are complex conjugates, and then there's another type. They correspond to the case where one P is here and one P is here. So they're kind of different, but you can check that the energy is still real. So this is really because of the elliptic properties of the energy function. And what you can check is that in this case, the energy is going to increase. So what's going to happen is that here we had half the dispersion, but now actually this curve is going to move up as we increase the interaction distance. And if we go all the way to Haldane-Shastry, something, again, really remarkable happens. So if we follow around what happens with these two solutions, remember that I'm decreasing kappa. So really, this half period here, the imaginary half period, is also going to go to 0. And in the Haldane-Shastry limit, it's strictly 0. So we know that the quasi-momenta must end up on the real axis. And what turns out is that the quasi-momentum that went left ends up precisely on the origin, and the one that moved right ends up precisely at the total momentum. So this is quite interesting because it means, firstly, that the energy is precisely the energy of just the second quasi-momentum. So what we have here, this situation is really very similar or the same as this situation up here. Here we knew that it was because of Sl2 symmetry, and now the spectrum shows us that there should be extra symmetries. So in terms of this picture here, the bound state curve has really, in the limit of Haldane-Shastry model, has merged onto this parabola here. So there must be some extra symmetry. And Haldane did these type of studies numerically for much smaller system size, but he kind of realized that this must be true. And then in Sl2, it was realized that actually there is a big extra symmetry algebra for the Haldane-Shastry model, namely the Youngian. I don't really want to go into the details, but here I gave the Drinfeld first presentation. So the point is that besides just spin lowering and spin raising operators and spin z, we now also have some sort of affine lowering and raising operators and some affine, I don't know, spin z, let's say. And we can write down explicit expressions. They're kind of bilocal, so they're a bit more complicated. But because of these extra lowering operators, the spectrum again reorganizes and we get bigger irreducible components. So what happens in the Haldane-Shastry limit is that, remember, these vertical strings were just Sl2 irreducibles, but now, because we have extra lowering operators, some Sl2 irreducibles are going to merge into one big Youngian irreducible, and that's what you see here. So in fact, this Sl2 highest weight vector is a Youngian highest weight vector. It's annihilated by Q plus and by S plus. But if you act by Q minus or something, kind of a suitable linear combination of Q minus and S minus, then instead you're going to get this thing, which was the limit of the bound states for Heisenberg and then Innocence. So the point is that we have lots of these extra symmetries, and because of these extra symmetries, we only need to know the Youngian highest weight vectors. And they are labeled by these patterns called motifs. And motifs are just, let's say, an increasing sequence of integers between 1 and the length minus 1. So I don't allow 0 modulo L, so that the integers are not equal and not neighboring. Remember, this was the condition that we had for scattering states. Yes? Yes? They have the same momentum and the same energy, that's right. The momentum, oh sorry, this motif, what I call the motif, it labels everything. So the motif actually here, so here the motif is just the value of the second integer. Here the motif is the two integers, which indeed are not equal and not adjacent. And here the motif is just the non-zero integer. So this motif is the same as this motif, in fact. And these motifs, they are just those. So now we know that these are just these integers. So you get the momentum by multiplying 2 pi over the length times the sum of all these integers, modulo L. No, right. Sorry. Okay. So yes, it is true. So QZ distinguishes between this guy and this, or these two, for instance. So yeah, that's right. Sorry. Okay. So the Youngian gives us these extra distinguishing operators. All right, so kind of to summarize and to really drive home the point, I hope. So for here, I've plotted the energy, now not as a function of momentum, but as a function of this deformation parameter. So here we have the nearest neighbor Heisenberg model. Then we turn on long-range interactions until we get all the way to Haldane-Shastry. And what we did here, just for length 6, because then the plot is not too complicated, not too messy. So here I've labeled all the points by their scattering and bound states and so on. So the integers for Heisenberg. And in blue, the scattering states, note that they are never equal or adjacent, and then here some choice for the integers for bound states. And so what you see is that as you go to the left, well, the energies go up typically, and then at some point there are crossing energy levels. This is quite important. It signals that the model should be integrable. There should be hidden conserved quantities that kind of mean that everything is preserved, even if the two energy levels get very close and become equal. And in the end, what can happen is that several energy levels coming from Heisenberg via Innocence for Haldane-Shastry merge. So this is again the point that I made before. So at such a mergel, what happens is that the top line is this Youngian highest weight vector, and the lower two are when you get these, well, as you can check here, they're always bound states. So for instance, 1, 4, and 2,5 go here. And below this, there is 155 and 115. So they're bound states. So the bound states kind of always come from below, as we saw in the previous plot. The bound state curve moves up until it hits the dispersion at Haldane-Shastri. And so we get this very nice correspondence, which we really checked very carefully for MS2. And at least at the level of the counting, it works for general M. So I'm quite convinced that it will work. We're currently checking this for MS3, but it's much more complicated. So the point is that for Heisenberg, we have scattering states labeled by these integers that are not equal and not adjacent. And as you go through Innocence, they will flow to Youngian highest weight vectors. Instead, bound states here, for which two of the integers are equal or adjacent, will flow to what we call affine descendants, or where we used at least a part of Q minus to get this vector. So this is actually, I think, a very nice principle. So one thing that I think it helps doing, and there's another thing that I'm looking at, is here we have Youngian representation theory, which is quite rigid, and we know the Drinfeld polynomial. So we really know everything about the representation theory here. So what we should be able to do is we should be able to use this representation theory here to organize the spectrum of the Heisenberg spin chain, where I want to think of the bound states as some sort of descendants. Of course, for Heisenberg, they're not descendants, but they're those vectors which in the Haldane-Shastri limits become affine descendants. And I think this is a very nice organizing principle, and I hope that it will not address completeness, of course, because I'm not going to prove that everything works well, but I think it gives a very good heuristic of writing down a way to organize, well, at least I hope that it gives a good heuristic for organizing the Heisenberg spin chain, where for each scattering state, you can kind of, from Youngian representation theory, compute precisely which bound states should correspond to it in the limit. So I think this is one point of view where you see that the long range perspective really might actually be quite useful, even just for the nearest neighbor Heisenberg spin chain. So continue. So I'm only talking about finite length here. I'm a kind of a finite. Sorry. So actually, all of these spin chains are known to go to a so level 1 Wess-Witten model. In the low energy limit is described by this with the same charge. Moreover, it is also known that the Heisenberg spin chain has an asymptotic Youngian symmetry. So if you send the length to infinity, there's actually an action of the Youngian. And here there is sort of another action of the Youngian. And this is work of Nina and Vincent long ago. It's related in the Q-deformed setting to this level 0 structure of level 1 modules and so on. So there's a very nice representation theoretic story. I don't really understand the details yet. So I think there will be some more. I believe that, in fact, in this case, there should be some, well, two actions of a Youngian, and I think this, so there should be some sort of affine Youngian, so sort of, let's say Q is one version of a quantum toroidal algebra acting there. So that's something that I kind of hope to be true, but I am not far enough yet to understand this. But right, I think there's definitely interesting things to be done there. All right, so we've seen that Haldane-Shastri spin chain is very special. We actually, the solution of the beta equations was just formed by these motifs. So it was very simple. Actually, solving the beta equations is easier than writing down something that formally looks like a beta equations that has those motifs as solutions. But that can be done. But let me tell you briefly about the algebraic background for this. The reason why Haldane-Shastri was so nice. And this is as follows. So there's a very nice algebraic picture, which is this one here. So this is like a cartoon of what happens. So Haldane-Shastri sits here in the right corner. But what we need to do in terms of representation theories, we need to start from some thing which is the symmetric group with extra generators called Dunkel operators, or at least they're represented by Dunkel operators. And together they obey relations of the so-called degenerate affine Hecke algebra. Now this algebra, I don't want to go into the details, but it has a representation on scalar bosons, which can be interpreted as being related to the trigonometric Calogero-Sutherland model. So this action here by Dunkel operators, if you symmetrize essentially, which is related to these bosons, gives rise to some bosonic model of particles moving on a circle while interacting in pairs. And this model is known to have commuting Hamiltonians, so family of commuting Hamiltonians, and it has exact eigenfunctions given by Jack polynomials, essentially. So this is a very nice algebraic story. Now, what you can do is rather than just looking at particles that move on a circle, you can give these particles spin. So let's give them spin 1/2. Then we have such a picture of particles with spin moving on a circle. And again, so this is what I would call the trigonometric spin Calogero-Sutherland model. Again, this model has commuting Hamiltonians, which you can write down. And moreover, it has Youngian symmetry. So this is something very special. Mathematically, this can be, so really this map is what's called the Drinfeld functor. So you associate to a representation of the degenerate affine Hecke algebra, a representation of the Youngian. And now what we can do is basically we can take a certain limit, which is called freezing, and Didina talked much more about it last week, which is like a semi-classical limit in which the particles move slower and slower and slower until they come at a halt at their classical equilibria positions, which are equally spaced. So you get, in terms of cartoons, you get such a spin chain. And this gives commuting Hamiltonians obtained by freezing from those here, as well as this Youngian action that I wrote down here, again, coming from this more general model by freezing if you do things carefully. And moreover, and this is kind of very cute, this Haldane-Shastri spin chain, if you look at the M particle sector, so with M down spins, so those are the kind of pink arrows here, then there is a connection between these down spins that behave just like a scalar Calogero-Sutherland model with only M particles at special values of the couplings. And that's really where the relation comes from, that we know the exact eigenvectors here as well. So in tiny bit more detail, I actually don't really want to go. So here's the trigonometric Calogero-Sutherland Hamiltonians. Here's the spin version. There's just this one here is replaced by a permutation. The rest doesn't matter. So maybe what I want to highlight is that the exact eigenvectors again involve, so it looks a bit complicated, but it's just a Vandermonde squared times a Jack polynomial. And this Jack polynomial is determined by the motif. So once you know the motif, you know these exact Youngian highest weight vectors, actually for any M. So it's a beautiful story and it really follows from this big algebraic picture here. I think I don't really want to go into details, but if anybody's interested, I'm very happy to talk more about it afterwards. So here's the summary of what I told you in the isotropic level. So we had these three spin chains: Heisenberg, Innocence, and Haldane-Shastri. Let me distinguish between three different notions. First is exact solvability. By this I mean that we can find some exact description of the spectrum, exact solvability, you know, so this is what, so the Heisenberg spin chain was exactly solvable once Bethe found the Bethe ansatz. So he was able to characterize the spectrum exactly up to solving the Bethe equations. Now there is a kind of a deeper, so this really kind of points towards the underlying structure, but I would not, so once we find this underlying structure, we know more. So this is what I want to call quantum integrable, and here I take some sort of microscopic definition. So Young-Baxter integrable, there's some quantum group underlying this model, also Youngian, as Fadeev and company realized, and via the algebraic Bethe ansatz, you can recover this exact solution of Bethe, and moreover, you can, via the transfer matrix, find higher Hamiltonians, which is like a sort of a macroscopic version of integrability, the existence of lots of. Sorry, I don't know why the microphone is unhappy. Okay, right. So let's compare this to Haldane-Shastri. For Haldane-Shastri, instead, we use this connection to the Calogero-Sutherland model, which I outlined before, and it gives a closed form description of the highest Youngian highest weight vectors. So this is simpler in the sense that we don't have to solve Bethe equations anymore, and we really have exact description of the spectrum. This came, as I showed you before, from an underlying degenerate affine Hecke algebra and a related Youngian symmetry. And again, it also gives this family of higher Hamiltonians. For Innocence, it turns out that you need to use both a Bethe ansatz and then you get some connection to an elliptic Calogero-Sutherland model. So you really mix the methods here and here. And then again, you get an exact description of the spectrum up to solving Bethe ansatz equations. This was first done by Innocence, and then we kind of find a kind of a better parameterization in which we can really take the Heisenberg limit, as I showed you. In fact, not just for the Bethe roots, but we can also really get for the MS2, for the two down the two spins down sector, we can really show that if you look at the wave functions here, they really limit to the Bethe ansatz wave functions here, and they limit to these Vandermonde squared times Jack polynomials here. So it's very nice. We really get a complete kind of match in the limits. And Innocence also has a conjectured family of higher Hamiltonians. There's a proof that the first two of them commute. So this is less well known than the situation of these sort of macroscopic integrability for Heisenberg and Haldane-Shastry, but I think well, things are happening here, and hopefully in a year or so this is settled. One really interesting issue here is that for Innocence we don't know an underlying microscopic integrability. So we don't know sort of an L operator or a Youngian action here, and this would be amazing. So I'm kind of trying, and a while ago I was hopeful that I would be able to solve it, but then I found that that didn't work after all. So, you know, this is a thing that I keep going back to. And no, I will go into that later. It doesn't. It's something, no, let me get back to this later. It's different. Oh, this is an exact computation. So what you really do is you write down some sort of extended beta ansatz, and then you do some elliptic trickery looking at poles and blah, blah, blah. And you really show that if you have a solution to the elliptic Algebraic model, then by specializing it to certain parameters, you get a solution, a wave function for the beta, for Innocence up to solving beta ansatz equations. So this is an exact computation, approximations there. And this we can do for general, I mean, Innocence already did this for general number of downspins. So this is very nice. So in principle, this part is sort of in principle known, but the details are much more complicated. The beta ansatz equations here are much more complicated. And they depend strongly on which solution of the elliptic Algebraic model you took, which itself already has beta ansatz-like equations. All right, so this is the kind of the summary of this. This is what I wanted to talk, tell you about this isotropic level. How much time do I have left?
About 10 minutes.
10 minutes, all right. So let me tell you briefly about both the partially isotropic level and actually another long-range deformation of Heisenberg type models. So we're going to change gears, and if you decoupled, then this is a good point to re-enter. So the following will be independent of the previous. So now let's consider the inhomogeneous Heisenberg XXZ spin chain. So, you know, this is something, so the Heisenberg spin chain, if we compute it, then we start with an R matrix. Here I take the 6 vertex R matrix. To be precise, I take the homogeneous gradation, so I can write it in terms of temporally leap, but the details are not so important. It obeys Young-Baxter, unitarity, and some sort of initial condition. And then you form the monodromy matrix, and you take its trace to get the transfer matrix T. Now, because of the Young-Baxter equation, we all know that these transfer matrices commute at different values of this spectral parameter U, and here the Z are my inhomogeneities. I work multiplicatively. So because of the Young-Baxter equation, we have a one parameter family of commuting transfer matrices. That's what this says here. Now, since we have commuting transfer matrices, we can get true spin chain operators by our favorite expansion of the transfer matrix. And a good point to do this expansion is where we can use this initial condition to simplify at least one of these crossings in the transfer matrix. So what you want to do is you want to choose your U to be equal to one of the values at the bottom here. So let's look at what would be the translation operator normally. We can now choose any of our inhomogeneities to take as a spectral parameter. And then pictorially, what happens is, well, you had this thing here, but now I take ZU to be ZJ. So over here, I get this situation. So this crossing opens up and it gives me this picture here. So from this picture, you can read off immediately an expression in terms of R matrices. I want to use mostly pictorial stuff here, but you can really write down formulas and check stuff. Maybe it's good to say that if I would take my inhomogeneities to all be equal, or let's say equal to 1 for simplicity, then what happens is, well, I again use this thing. So all these crossings kind of open up, and instead you see that if all these crossings open up, I just get the operator which shifts by 1 to the right periodically. So this is just the usual shift operator. But here we have L different shift operator, kind of not really shift operators, but L different things which all deform the shift operator. So sometimes these are called scattering operators. Sometimes I think they're also called Young-Baxter. They all commute, and they don't have the property that the Lth power is 1, but instead, if you multiply all of them, then this is the picture. Now by unitarity, you can kind of open up all these crossings here, and basically none of the lines cross, so you just get the identity here. So instead, these operators, all their products are 1. Now, if you take the homogeneous limit, then all of them become the same. So you get the usual relation that the nth power of the, in that case, translation operator is 1. And that's why we get the notion of a quantized momentum in that case. All right, so let's be a bit more brave and go to the next order in the computation. So what we want to do is we want to take the logarithmic derivative of the transfer matrix at this special value of our inhomogeneity. So let me compute it as the derivative with respect to the first argument at zj times the inverse of this scattering operator. So pictorially, the inverse of this thing is just if I flip left and right. So this is this picture here at the bottom. And now this derivative here, well, we have a product of things that all depended on u, so we get a sum of all the derivatives. Let me denote this derivative by a dot. Okay, so then the derivative can either be to the left of the value or at the value of the inhomogeneity that we plugged in or to the right of it. So these are the pictures that we get for the Hamiltonian. So it's either, right? So these are the three possibilities basically. So we can continue our computation. So note that here, for instance, we have precisely an instance of this unitarity. So I can certainly unwind this stuff until I get just a crossing that would look like, you know, there's a line here, and then there's a dot here. So it is a composition of the R matrix and the derivative of an R matrix. Now we can compute a bit more about this. It turns out that this R matrix times the derivative of the R matrix is just the derivative of the R matrix time at 1 times a function, which here I call V. It's like a potential. So it is basically the product of the two inhomogeneities, and then here's like a little Q van der Monde times a Q inverse van der Monde, if you wish. So what you get is the following, up to some constants, you get this potential normalized times some sort of strange long-range interaction where the jth spin, remember this was the jth Hamiltonian, so the jth spin moves to the left until it's at I+1, then it interacts via the usual local Hamiltonian, and then it transports back. But here the transport is always via these R matrices. Then there is another term, so I'll come back to this in a moment. Then there's another term. If J was to the right of K, then what's going to happen is that J is going to go periodically all the way to K+1. It interacts and it moves back. So basically this is just like this, except that you use periodicity. So J always wants to go to the left to interact with this other thing. And now the strange case is this one here, where J interacts with itself. And actually that's what it does, if you do this carefully. So what happens is that J goes to the left, then it interacts with itself in the future, it goes to the right to interact with itself from the past, and then it finishes. So this looks a little bit weird, but what you can again write in equations. What you do is you write this temporary leap generator, or more generally your derivative of the R matrix, as a tensor product of two. You take a basis of operators on one side, you write a tensor product of these two bases on one side with some coefficients, and that's how you can kind of split the interaction into two things. So I can write down the details later if somebody's interested. Maybe. Sure, you could. I haven't, but you can, yeah. Right, so let me take the homogeneous limit here as well, just to check that everything is correct. So remember, in the homogeneous limit, all these crossings just open up. So what happens here is that in the inhomogeneous limit, all these crossings open up. So basically, nothing happens except that here I interacts with I+1. For all I lower than J. Here, J interacts with actually J+1, no longer with itself. And then here, K interacts with K+1 for all the K larger than Z. So you see and then these coefficients all become 1, of course, if you took all the Z's to be 1. So this is just the usual XXZ nearest neighbor Hamiltonian. So this is a consistency check. Okay, so I just wanted to show that actually normally we spin chain as, computational tool. It's natural from the 6 vertex point of view. It's kind of nice from geometric representation theory, if you wish. These inhomogeneities are equivariant parameters. If you like supersymmetric gauge theories, beta gauge correspondence naturally has inhomogeneities. I forget affected twisted masses or whatever they're called. But so there are actually some various reasons to introduce them. Also in proofs of completeness is good because you lift some degeneracies for generic inhomogeneities. But what I want to propose is actually this is kind of a nice model by itself for finite size. Of course, if you're going to send the length to infinity, then you have to think very carefully. You kind of probably don't want to manage infinitely many different indeterminates unless you would want to do something like McDonald's where but I don't know if that's possible. So usually that's where you take, for instance, the homogeneous limit. But for finite size, this inhomogeneous XXZ spin chain, there are lots of these Hamiltonians and they look quite nice. And of course, so here is the Hamiltonian again. We can find its exact spectrum using the algebraic ansatz, up to solving beta ansatz equations, where then the e to the I p like momentum times the length is deformed into a product where all the inhomogeneities enter. So this is the recap of what I just showed you. Now this model is quite complicated. It has this complicated self-interaction. There's some sort of periodicity and so on happening. The Q-deformed Haldane-Shastri spin chain actually turns out to look very similar to this inhomogeneous Heisenberg spin chain, except that the only interactions that happen are these kind of fairly simple ones. Namely, the Q-deformed Haldane-Shastri spin chain is a sum over pairs of sides where there is the same potential function that we had here without the normalization. So this function here times just the interaction where J moves to the left to interact with I, and then it moves back via our matrices. The difference is that to really get the Q-deformed Haldane-Shastri spin chain, we have to not take the homogeneous limit, but instead we have to evaluate these ZJs to jth powers of the lth primitive root of unity, or the primitive lth root of unity. Okay, so this is a special other point. Notice that this is also a periodic point. Here it is still true that if you take ratios of these things, they only depend on the difference of the coordinates. So it's kind of nice from that point of view, and it's consistent with periodicity. If we take q to 1, then this function here just becomes z prime minus zz prime over the difference squared. And if you write it in terms of these things here, you just get this 1 over sine squared that we had for Haldane-Shastri. If you take q to 1 here, then actually what happens is that this just becomes 1 minus the long distance permutation. So this is a true long range model, of course. And so here's the Q-deformed Haldane-Shastri model. So it looks like a bit of a monster, but actually once you've gone through inhomogeneous XXZ, it's actually a little bit simpler than inhomogeneous XXZ. And accordingly, actually its spectrum can exactly be found via a connection to a Q deformation of these Calogero-Sutherland models, which are known as Ruisenaar's McDonald models. So, and we have this exact spectrum in closed form. So here is the picture. I don't really want to go in details because of time, but basically, if instead of the degenerate affine Hecke algebra, you start with the affine Hecke algebra, then you either get a scalar model or you can introduce spins, then you can freeze, then you get this spin chain, precisely with the Hamiltonian that I showed you before. So that's really how we compute it. And again, its downspins behave precisely like a fewer particle special value of the couplings version of this scalar model, which has exact eigenfunctions that are McDonald's polynomials. So for Q-deformed Haldane-Shastri, we also have a closed form description of the highest weight eigenvectors. In this case, it's quantum loop highest weight eigenvectors. And so there's sort of like a Q-deformed van der Monde squared, if you wish, the symmetric square of the Q van der Monde times a special point of the McDonald's polynomials that are known as quantum zonal spherical functions. Now, let me, for the more minded people, mention that actually this kind of highlights, this is really, we can reinterpret this in terms of affine pure probability. And I want to advocate this as the point of view for these long-range spin chains. So here, there's a map that sends a module for the affine Hecke algebra to a module for the quantum loop algebra. And if you're careful, then the center of the affine Hecke algebra acts by symmetries, and that's where the Hamiltonian comes from. So this is what's known as the, well, it's kind of like the Q deformation of the Drinfeld functor. It was studied by Chari and Presley, but actually earlier by Bernard Godin, Haldane, and Pasquier. And so this is the spin version of the McDonald's model. We understand this very nicely. We have exact eigenfunctions here via partial symmetrizations of non-symmetric McDonald polynomials. But so this map is really the Schur-Weil functor, if you wish, the Schur functum, the quantum affine version of the Schur functor. And this is a very special case of it in which I took the vector space to be one-dimensional, so there are no spins. But in fact, I can do this for any GLK module, and there's a very nice story here. And this is why I come back to Philippe's question. So if instead here, rather than working with the representation of polynomials with Y operators, if you take the simpler representation where you just act by multiplication, which is also an affine Hecke algebra module, then here the quantum loop action would be given by the usual inhomogeneous XXZ spin L operator. In that case, the center is trivial. It's just multiples the identity. So instead, what you could do is you can take the trace and look, then you would get to these inhomogeneous XXZ models. So rather, the double affine Hecke algebra really plays a role here, where we get either this trigonometric spin Ruisenaar's McDonald or inhomogeneous XXZ, depending on which of the two we do. And if we here really take Daha, then here we should get somehow an interplay of both, which is what I mentioned before. There should be some role for a quantum toroidal algebra here. Right. So that was a little bit of representation theory. Let me just mention Q-deformed Innocence is not known. I would love to know it because that would be a deformation which really goes in between somehow these two Schur-Weyl dual, Cherenkov dual models. So we have, maybe Heisenberg XXZ if I take homogeneous, or maybe it should be some inhomogeneous Heisenberg XXZ. And on the other side, this Q-deformed Haldane-Shastry model. So I would really like to know what happens in between. I think it would be very interesting, maybe not so much from a physics point of view, but I think it would really teach us a lot about what the structure of, what it means to be integrable. If we would find this, like a version of an L operator here, that would be amazing. It would somehow allow you to interpolate between the two Cherenkov kind of Daha dual models here and here. And right, so here's the big picture. So just to wrap up, what I showed you is how to go from Heisenberg via Innocence to Haldane-Shastry. I also showed you how to Q-deform this by going from degenerate affine to affine Hecke algebras. And then I showed you that the Heisenberg XXZ is actually also sitting in another family of long-range models via inhomogeneities. And what I really think is that by this long-range picture, what I want to do is conquer the world of long-range spin chains. And I think that this will show us, even teach us a lot about these nearest neighbor Heisenberg spin chains. And underlying all of this should be an analogous map for quantum many-body systems with or without spins via freezing and so on. So I think a lot of things are to be happening here. I'm also working on at least some elliptic things, but of course they're much harder. So at least I hope to have shown you quite an exciting landscape and for your attention.
Just a tiny question. You had among the final slides, you had a conjecture, which is the only thing which is not unknown.
Right. Yeah.
So this means that you have a conjecture for the potential, such that if you diagonalize the states, you see that there is no level crossing, there is no level split.
No, it's much weaker. So what you can do is you can get an elliptic. Oh, sorry. You can get an elliptic function by forcing, like putting an imaginary period in here. So you just take an infinite sum to kind of force this function to be imaginary periodic, and then you get some sort of zeta minus zeta, which if q goes to 1 becomes Weierstrass p as a derivative of zeta. But what we don't know yet is the precise long-range spin interaction. So remember, here it's much more subtle because I also need to know what happens here. And so I know so the conjecture is very weak. We just have a proposal for what we think would be the potential here. At least it will limit to the right potentials there and there. But it does not. So what you could do, of course, is just take this Hamiltonian and put our conjecture for the potential in here. But you see that these long-range interactions, they're actually multi-particle interacting. They're incredibly complicated. For Haldane-Shastry, for Q-deformed Haldane-Shastry, we were lucky. We had all this representation theory with it, which allowed us not to compute any actions of the Hamiltonian, but just be very clever and understand its spectrum. So in fact, if I take the one-particle eigenvectors of Q-deformed Haldane-Shastry, this is not translationally invariant in the standard way, so you don't get Magnons. They're more complicated. I can find them using some sort of representation theory type of trick. It's not hard, but I am not able to compute actually the action of the Hamiltonian on these eigenvectors directly. This is extremely hard. So even for the one-particle vectors here, it is kind of, it seems, well, maybe if we're very, very courageous, we would be able to find a potential corresponding to such a Hamiltonian with our conjecture for the potential. But it is, so trying to do coordinate-based ansatz seems very, very hopeless.
Do I understand correctly that you start with the isotropic 6-vertex model, then you Q-deform it, then you construct inhomogeneous transfer matrices from which you get the Q-deformed Haldane-Shastry model. And then Q to 1 would give you the isotropic, the usual Haldane-Shastry model. Is that correct?
No, well, okay, so 6-vertex is already Q-deformed, right? So not quite. So what I wanted to do, so actually this Hamiltonian, really, to get it, I use this picture, which I think I showed on the next page. So I use this kind of quite abstract representation theory type of thing to take this representation of this algebra here, then I get these McDonald's operators, and then I do this thing called freezing, and this is how I really compute these Hamiltonians. Here, these Hamiltonians, if you've never seen anything like it, they look quite intimidating. What I wanted to do is I wanted to show you that they may be a bit intimidating, as I kind of answered to Andreas' question, but in fact, there is a Hamiltonian which kind of implicitly we all know, just the inhomogeneous version of the XXZ, which is much more complicated than this Q-deformed Haldane-Shastri. But the L operators would be quite different. So no, there's not a simple, from this L operator here, I cannot get this Hamiltonian.
Okay, thanks.
Jules, the commuting transfer matrices generate an abelian subalgebra of whatever your underlying algebra is. How does that compare to, say, the abelian subalgebra generated by the Y operators in
Right.
affine Hecke?
So what we do in so over here we have some quantum loop, or in the Q going to one limit Youngian symmetry. There is indeed there are two abelian subalgebras. One is generated by the quantum determinant. It's actually the center of the this quantum loop algebra, and that is where these commuting Hamiltonians of the spin McDonald model come from. Okay, so this is the center, and that's why the whole algebra acts by symmetry. So there will not be an algebraic beta ansatz. Instead, we need something like this connection, like I outlined here. Now, what you could, of course, do, and this is something that we're doing with Didina and Gwenaëlle Ferrandro and Fedor Levkovich-Maslyuk, is you can also look at this L operator here. It looks like an inhomogeneous L operator, but with Y operators instead of inhomogeneities, but formally they commute, so we can do all the computations like before. And what you can do is instead take its trace. Then you get a abelian subalgebra that is like the beta algebra of this action of the quantum loop algebra here. And what we are working on is indeed what you can do is you can also understand its spectrum. So this is quite nice. If you introduce a twist, for instance, and you send the twist to infinity, this will give the Gelfand-Zeppelin basis for this quantum loop symmetry here. So there's a very nice story that you can do by kind of changing which abelian subalgebra I take here, whether I take just the center or this beta algebra. And one thing that we don't know yet, but it should be possible, is if we take this transfer matrix here, we can also freeze, and we should be able to get some extra Hamiltonians of this thing here. Remember, this is a very big symmetry algebra. So in fact, what I'm saying is that there are other Hamiltonians that commute with all of these here and with each other, but they don't commute with the quantum loop action. Those would be some sort of extra Hamiltonians, which would be diagonalized by algebraic beta ansatz with Y operators instead of inhomogeneities, and formally you can play the same game. And what we would like to do is get explicit expressions here. In fact, I think that some of them will be limits of these charges proposed by Dietrich and Innocence if you would go to the isotropic Haldane-Shastri model. So right, so there are two abelian subalgebras.
Thank you for your nice talk. Again.